reagents. So limiting reactant or limiting reagent, they both mean the same thing. Now, this may seem like a really silly principle, but let me share it with you. See if you're on board. When you run out of something, you can't do it anymore. No, this is really dumb, but if you run out of something that you're doing, that you're playing with, that you're doing whatever, if it runs out, then whatever you were doing, you're done. My son loves burbujas, bubbles, loves them. There's a finite supply of bubble mix in the little bubble container, right? It doesn't matter if I have 2 or 3 or 4 of the little circly things that you blow the bubbles out. When that dip is done, bubbles are no longer there. So if I run out of one of the ingredients in my bubble producing mix, then I no longer can produce the bubbles. Agree? Now, this is probably a fairly lame example, but this is how it works with reactions. If you ever have 2 reactants or reagents, and they're forming some product, when one of them runs out, the reaction stops. You can't keep going because when you run out, you are done. Does that kind of make sense? So as simplistic as that principle is, it matters to us because as soon as we run out of one of our reactants, which we call the limiting reactant, we no longer can produce product. Now watch this for a second. I'm going to emphasize this for a second. So let's pretend that I have a reaction and I have let's do it this way. I have a green and I have a red, and together they produce GRED, right? So the reaction is really simplistic. It's a 1-to-1 ratio. For every 1 green and 1 red, I produce 1 GRED. Now, all of us understand what I'm just talking about right now in terms of the ratio. If we don't have enough of one of the 2 of them, the reaction will stop. Now, if the reaction has to go in a 1-to-1 ratio, and I have 5 of this and I have 10 of this, do you realize it's going to go like this? GRED, 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 4, 5, and then there'll be no red and just green left over. And guess what I can't produce when I have just the green?
GRED.
I can't, it doesn't matter. I can have a billion green, but I have so many green. It doesn't matter because as soon as you run out of one of your reactants, you are done. So if I were to try to figure out how many GRED I could form, and I had 5 of this, and let's pretend I have 1,000 of this, right? How many GRED will I actually be able to form? I'll only be able to form 5. Why? Because there's only 5 red, right? Now, what if I were to do the math starting with my green? If I start with my green, I'd be like, I should form 1,000. But guess what that is? A lie. Why? Because I am pretending if I have 1,000 of this, then I must have 1,000 of this to react with. And if I only have 5, that's not truth. Which leads us to a really important thing. First of all, let me define for you this, but before you write anything down, let me tell you the important thing. Whenever you try and figure out the amount of product, you must always use the limiting reactant as your starting point. Let me define for you this, and I'll define that as well. So what is a limiting reactant or a limiting reagent? It's the reactant that gets words are so hard, that gets used up first in a reaction. It's the reactant that gets used up first in a reaction. This is worthy of a little star. Now, if one thing gets used up, we call it the limiting reactant. The thing that we have excess of, oddly enough, we call it the excess reactant. So the excess reactant is what we have left over of the other reactant. So limiting reactant is whatever reactant we use up first, and the excess reactant is whatever we have left over. Now, the starable, boxable, underlinable, whatever you do to make things seem really important statement would be this. You must always start with your limiting reactant when you are trying to figure out the amount of product. You must always start with your limiting reactant when you're trying to figure out the amount of product. Can you put in parentheses next to amount of product? Can you write the words theoretical yield? Theoretical yield.
Like in parentheses.
Yeah, that'd be good. So you must always start with the limiting reactant when you're trying to figure out the amount of product or the theoretical yield. Now, can I affirm this to you here? Do you realize that it's important to be able to figure out mathematically prior to doing a lab how much theoretically we should get? We call that the theoretical yield or the amount of product. In fact, anytime you do a calculation and you take your limiting reactant and you figure out how much of the product you should get, we call that the theoretical yield. Just out of curiosity, if we were to, prior to a lab, take the reactants and do the calculation and figure out how much of the product we should get, or the theoretical yield, how likely are we to get that exact amount when we actually perform the experiment? Do you think?
Sorry, can you repeat that?
So let's just pretend prior to doing an experiment in the lab, I'm doing a reaction where I take two things together and I form a product. So prior to doing the lab, I set about figuring out the theoretical amount I should get, the perfect amount. What are the chances when I do the lab that I'll get that exact amount?
Probably faint.
Yeah, I go with 0 chance, because even if we're like incredibly careful, you realize that even like things like putting stuff into a weighing boat and then putting it out, aren't there particles that get left behind? Or when you're stirring, maybe some of the stuff gets left on the edges. If not at a macro level, at a microscopic level, certainly. And if you have enough of a sophisticated machinery to do the measurement, you're never going to get what you theoretically should. I mean, theoretical yield is like the butterfly kisses and rainbow unicorn world, right? Where everything's perfect and you figure out, hey, here's the amount of reactant I have, my limiting reactant, here's how much product I should have, boom. We need to be able to figure that out, though, because that gives us a pretty good idea of what we should be expecting in a particular reaction. Now, how do we figure out the limiting reactant? And it's all about ratios. And let's do that. So I'm going to shift over to doing a problem on the board. And can I encourage you guys to write this example down, and we'll use that for teaching this. So we've used this before, so I'm going to use this right now. Let's do H2 plus O2 goes to H2O. This is a gas. This is going to be a gas. This is going to be a liquid. I've just gotten in the habit of putting the states of matter in there, even though it doesn't necessarily matter a whole bunch in terms of our problem. The other thing you need to be aware of, and I cannot emphasize this enough, I've said this before already, you need to have a balanced equation in order to solve problems, right? This is even more important now. So this, while it's a delightful equation, in order to balance it, don't we have to put a 2 right here and a 2 right here? If we don't have that, then anything we do after that's going to be wasted time. Yes, ma'am. Now we got that on film. That was me like looking before I actually written down. Yes, thank you for catching me on that. So let's say I gave you this. Let's say I have given 8.00 moles of H2. Actually, you know what? Let's do 7. Sorry, I know that you can't erase. I know it's terrible. I'm gonna do 7. 7.00 moles of H2 and 5.00 moles of O2, which is the limiting reactant, abbreviated by LR. Now, I'm going to wager that all of you can do this in your heads without doing any mathematics. Because watch, doesn't this recipe call for 2 moles of hydrogen for every 1 mole of oxygen? Which of these 2 do I not have enough of? If I have 7 moles of hydrogen and 5 moles of oxygen, which one here would I run out of first if I was trying to do that ratio? Wouldn't I run out of hydrogen? Because if I just do the math in my head, if I have 5 moles of oxygen, isn't the ratio 1 mole of oxygen for every 2 moles of hydrogen? Wouldn't I need 10 moles of hydrogen? Don't I only have 7? So we can mathematically do that. If you're like a pictorial learner, let me just show you this. This may or may not help you. Let's pretend that I have hydrogen with my H2, and these lines are going to represent moles of hydrogen. 1, 2, 3, 4, 5, 6, 7. That's the number of moles of hydrogen. And for oxygen, I have 5 moles. 1, 2, 3, 4, 5. Now, according to my equation, doesn't it say I need 2 moles of hydrogen for every 1 mole of this? So if I was just seeing the reaction go, it would go like this. 2 moles of hydrogen go with 1 mole of oxygen. Yeah? Then 2 moles of another hydrogen go with 1 mole of oxygen. Then 2 moles of hydrogen go with 1 mole of oxygen. And guess what we run out of here? We run out of hydrogen. We don't have enough hydrogen to keep that 2-to-1 ratio. Are you with me? So wouldn't that make the limiting reactant hydrogen in this case? And if we ever wanted to figure out the amount of water that's formed, we would have to start with the amount of hydrogen they've given us in the problem. Now, I was deliberately giving you a pretty straightforward problem because I want you to be aware that all of the math we're doing is all ratio based, and you could probably do most of the stuff in your head. However, when we get to a little more complex problems, this becomes a little more tricky. So let me show you a really neat trick that I'd seen before. I never really paid attention to it, but I saw it again 2 years ago. A student showed me this, and couldn't we do it this way? And I'm like, that's pretty fantastic. So I'm going to show you this Jedi trick. Understand that it's a trick to allow us to figure out what the limiting reactant is. So here's what we do. We take both of the reactants, and it has to be in moles, because isn't our equation written in moles? What happens if they give us the reactants instead of moles, give us in grams? We've got our first step hasn't to be to convert to moles, but they've given it to us in moles already. So I'm going to do this. I'm just going to write the number of moles I have of hydrogen, and I'm going to write the number of moles I have of oxygen kind of on top of each other. Not like physically on top, but leave some space in between. And here's the trick. If you ever want to figure out which is your limiting reactant, you take each of the reactants' number of moles and you divide by the coefficient of that reactant. And whatever you have less of, that's your limiting reactant. So let's do this together. 7 divided by 2, would you agree with me, is 3.5 moles. Yeah? Wouldn't this be 5 divided by 1? So wouldn't that be 5 moles? Say yes.
Yes. Yes.
Isn't this smaller?
Yes.
This is smaller, therefore this is my limiting reactant.
Wait,
No.
why did you divide by?
The coefficient for hydrogen is 2. The coefficient for oxygen is 1. So watch. These numbers here are just tools for us to figure out what the limiting reactant is. And by the way, it's kind of a fun trick here. If you wanted to figure out how much excess you have, because remember, if this is my limiting reactant, doesn't this by default become my excess reactant? If I want to know how much excess, what I can do is I can say, I can take this 5 and subtract the 3.5, and that means I'm going to have 1.5 moles of excess. Does that make sense? I have 3.5 moles here needed, 5 moles here needed. But I'm going to hold off on that. Can we hold off on the mathematics of it first for a minute? Yeah? Because we're not going to be doing excess right yet. But this is the number I care about. This right here, this is our Jedi trick. Right? So we're not using these numbers to do any more math in the problem. But didn't I say that in order to figure out the amount of H2O that we could form, must we start with the limiting reactant? So what if in this problem it said, which is the limiting reactant and what is the theoretical yield of H2O? Let's say that was the problem. Now, didn't I share with you that you must always start with the limiting reactant in order to figure out the amount of product or the theoretical yield? Theoretical yield kind of sounds scary, right? But isn't theoretical yield just the amount of product? And typically it's the amount of product in grams. Unless they specify, tell me the theoretical yield in moles, we're going to have to go to grams. So watch, and this is kind of a big deal with this. Isn't this my starting point? Moles of H2. So couldn't I then go, all right, I'm going to take my 7.00 moles of H2, and won't I try and go, if we look at my equation, won't I try and go from here to here? So I'm trying to get to the product. Incidentally, isn't that identical to what you guys did in your homework? This right here. Remember? So right now we're starting at moles of A, and we're trying to go to moles of B, and then we're going to get to the grams of B. So this is identical to what you guys are doing homework-wise. Let's just do it. So I need to, in order to go from one thing to another in an equation, mustn't I use the mole ratio? Which in this case, isn't it 2 moles of H2 for every 2 moles of H2O? I'm pretty certain that if you look at this and you go 2 moles of H2 and 2 moles of H2O, isn't that essentially 1-to-1? So we can cancel it out. But for right now, just so you see where we're getting the numbers, I'm going to leave the 2 and the 2 in there. Then, as with all the homework problems, once we cancel the moles of H2. Once we have moles of H2O, we want to get to grams of H2O, right? Must we use the molar mass of H2O? Now, with the molar mass of H2O, it's always per 1 mole of H2O. And I want to be really clear here. See this 2 in front of this H2O? It only impacts us when we're doing the mole ratio stuff. Don't you dare go, oh, well, there's 2 H2O, so I'm going to double my molar mass. No. Can I get a head bob if that makes sense? That 2 right here, yes, it's important, but it's important because we wanted to get from H2 to H2O. But other than that, we leave that alone. So in order to get the molar mass of this, wouldn't we have to take the molar mass of 2 hydrogens and 1 oxygen and add them all up? Now, I've done this a lot of times. Oxygen is 16, and each oxygen is 1.0079, which rounds to 1.008. So I get lazy and I say, well, 1.008 plus 1.008 is 2.016 plus 16, right? Wouldn't that be 18.016 or 18.02 grams of H2O? I just rounded to 4 significant figures. That allows me to cancel my moles of H2O. And since my 2's cancel, wouldn't I just be multiplying 7 by 18.02? Can someone do that for me, please?
Oh, sorry, so I was 7.
Yeah, I was going to say that should be a much bigger number.
126.14. I think 8.02.
Now, I would say this. This number, while it is a number that works, 126.14, didn't I have only 3 significant figures in my original problem? So mustn't I then reduce this down to what? 126 grams of H2O. From the very beginning of the year, we've said that significant figures are a thing. So we've got to keep on track with that.
Wait, I thought we used the one that has the most significant figures in the.
Not most, least. You always use the least.
So we're not doing exponents.
Well, okay. So what Emma just asked right there is, do we have to use exponents? No, because right here I have 126, right? If I already have an exponent in the problem, which occasionally will happen, then you need to make it into good form, as we like to call it. But there's no reason to make this 1.26 times 10 to the second, because how does that make my life better?
Is it wrong?
No, not at all. Not at all. So if that's your thing and you're like, you know what, exponents are my favorite, and you decide 126, way too simple, and you go 1.26 times 10 to the second, that's right. Now, let me show you this. And I want you guys to kind of work this along with me, shall we? Okay? I'm going to change the numbers on this, okay? And I want you to work it through with me. So same problem, but instead of moles of H2 and moles of O2, what I'm going to do is I'm going to give you grams of both of them. So what I'm going to do is I'm going to give you 8.310 grams of H2 and 26.00 grams of O2. And I want to do the same 2 things. Figure out what the limiting reactant is, and then figure out what the theoretical yield is. Now, O2. Here's the thing. Can you look at the ratio in the equation and compare the grams of each of them to each other? You should probably say no on this, because what is the equation written in? Moles. And what's really amazing about this, you see how we have clearly more grams of O2. But are you aware that if I did this, do you realize the molar mass of O2 is 32? So wouldn't this be less than 1 mole? Isn't the molar mass of H2 around 2? So isn't this like 4 moles? So isn't this more moles than this is, even though this is more grams than this is? Do you understand? That's because O2 is much, much heavier. Are you with me right now? So if you, and this is where your brain needs to spark, the only units you can use in your equation have to be moles. So if they give you grams, what's the first thing you do? Always, always, always. Convert everything to moles. Because if they give you grams to start with, there's no way you're using an equation with grams. It should be automatic, and the periodic table and molar mass should be your friend. So I'm going to do this over here so I have a little more room this time. Similarly, well, just like we did before, I'm going to go 8.310 grams of H2. But won't I first have to convert that to moles? And similarly, I'm just going to leave some space and do it underneath here. If I have 26.00 grams of O2, again, I'm going to have to convert that to moles. Now, we've done this a few times before, so let me just put the values in here. 2.016 grams of H2 for every 1 mole of H2. Are you okay with this being the molar mass of 2 hydrogens combined? Right? And then down here, we have 2 oxygens, and each oxygen, I'm rounding to 16.00. You realize that oxygen, if you look on your periodic table, some of you have 15.9994. You can use that. Your number will be slightly different than what I get here, but that's still okay. 15.9994 or 16.00, they're about the same things. I'm going to use 16.00 because that gives me this number of grams of O2 for every 1 mole of O2. Can someone tell me math on this? 4.122 moles of H2. And is it okay, since they have 4 significant figures here, is it okay if I just put the 4 significant figures right here? And then what do we get for the moles of O2? 0.012.
I mean,
0.8125. Big difference. 0.8125 moles of oxygen. Now, this is actually what we have, right? So if we want to do any further calculations, we're either going to start with the 4.122 moles of H2 or the 0.8125 moles of O2. One of these two is going to be my starting point. Remember our Jedi trick? What's the trick? Divide by the coefficients, right? So even though this is the number I will, or this is the number, one of these two are the numbers that I will actually work with in the remainder of the problem, I'm going to use my trick first. So wouldn't I divide my H2 by 2, and wouldn't I divide my O2 by 1? And if I did that, what do I end up with my H2? 2.061. And what do you end up for moles of O2? 0.8125. Pretty sure that this is smaller, isn't it? What does that mean then? This is my limiting reactant. Yeah? Now, are you aware that in the problem I just gave you on the board, do you see how I started by asking you to figure out the limiting reactant and then said figure out the theoretical yield? Even if I didn't say find the limiting reactant, wouldn't you be forced to do that if you wanted to figure out the theoretical yield anyway? So a lot of problems, what they'll say is they won't say find the limiting reactant and excess reactant first. They'll just say, tell me the theoretical yield of H2O, and on your own, you're going to have to do this step. Now, what's really important here is, isn't this the number I'm starting with right here, the moles? Now, you could go all the way back to grams, couldn't you? But didn't you spend the time getting to moles already? And isn't our equation written in moles? So why would we go back to grams? There's no reason to. And in this problem, they're asking us for the theoretical yield of H2O. So wouldn't we now just be going from moles of this to moles of this? And that goes back to what we were doing in our homework. Moles of A, grams of A to moles of A, moles of A to moles of B, moles of B to grams of B. What we were doing in the homework last night. So I'm going to take this number right here, and that's going to be my starting point for this. 0.8125 moles of O2 is my starting point. Isn't the ratio between O2 and H2O 1 to 2? So can't we put that into our equation? So I'm going to just keep on working on my table, and I realize I've not left very much space. So I'm going to write really tiny. So I'm just going to go 2 moles of, let me make this neat, 2 moles of H2O on the top and 1 mole of O2 on the bottom. That's just following this ratio right here. Moles of O2 cancel, and then aren't I going to have to do the exact same molar mass that I used in the previous problem for H2O, but when I just go 1 mole of H2O on the bottom, and I believe it was 18.02 grams of H2O, moles cancel, and now the math, isn't it this times this times this? Someone have that for me?
29.2825.
29.2825?
Yeah.
Wonderful. Now, let's get to the matter of significant figures. Didn't both of mine originally start with 4 significant figures? These right here, these are called exact numbers. The ratios, they are exact numbers, so is this number right here. So we don't include that in our calculations. But so that wouldn't that mean that we have to cut off right after the 8? So my answer would actually be this, ignoring that. 29.28 grams of H2O. Yes, sir. Okay. Any questions on what I just shown you? So limiting reactant is a pretty, go ahead. Did it come back to you?
Yes, sir. So you said we don't use, since there's 1, and we don't use that as the significant figure, like counter example, I guess.
Correct.
But you never mentioned about anything about the ratios being like 2 and 3.
Those are also exact numbers. So this, good question. So if I look at this here, 2, 1, 2, that's exactly 2 moles for exactly 1 moles reacts exactly 2 moles. So if you wanted to, on the 2 to 1, you could write 2.00000 as many times as you wanted to. That's why we don't include that as part of our limiting factor for significant figures. Okay, so I'm going to do this here, and this is going to be the final part of the lecture portion. I'm going to give you guys an example that I want to do on your own. We'll do it on the board together after you take a shot at it. But I've written the problem up at the very top of the board. Yes, ma'am.
What is that? The middle one? Yeah.
2 moles of H2O. Yeah, my handwriting, or my textbook, or my board writing is pretty awful. Sorry. Should I hold off erasing or? Okay. So what I'm going to do is this, and there is something you have to notice when I do this problem before you start. This is the equation now. This is the problem I want you to do. I'm going to give you 26.0 grams of N2, 3.901 grams of H2, and ask you for the theoretical yield of NH3. Here's the thing. You can't work with that problem unless you have an equation. Would you agree?
Yeah.
So let me give you the equation. The equation is N2 plus H2 goes to NH3. This is a gas, this is a gas, and this also is a gas. There's something that you must do before you start this problem. This is going to be my stopping point for the video, and for homework, you guys are going to do the limiting reactant practice.